Hello everyone and welcome back to Thermo Shorts, where we've been talking about Rankine cycles. So we just went through this Rankine cycle problem and we found that the thermal efficiency was a disappointing 28.4%. So now we're going to ask the question, how do we improve Rankine cycle efficiency? Here we can see that we got 28.4%, but the maximum efficiency, the ideal efficiency, is almost 30% higher. So how do we get better? Maybe before we answer that question, it's worthwhile to ask the question, why do we want to improve thermal efficiency? And it's easy to see that this is a win-win proposition. So first, if we can make things like power plants more efficient, we save money. Second, if we can get the same amount of power out and reduce the amount of heat that we put in, which will reduce the emissions from that power plant, well, it's easy to see how that's beneficial too. Even if we take a simple model, like this Carnot efficiency model, there's two things I see from this equation that I can do to improve thermal efficiency. I can increase T hot, so I get 1 minus some smaller number, or I can decrease T cold, so again, I get 1 minus some smaller number. How can I increase T hot? Well, the first thing I can do is I can superheat the fluid that goes into my turbine. So remember, we need steam to go into our turbine. So I can go from coming out of my boiler being a saturated vapor to something that's got more enthalpy in it, like a superheated vapor. By doing this, I'm increasing the temperature that I'm adding heat into the system. And it turns out that that increases my thermal efficiency. Another thing I can do to increase that temperature of heat addition is have a supercritical fluid. Now remember, the critical pressure is the pressure that just kisses the top of this vapor dome. So if I go to some supercritical pressure, then I miss the vapor dome entirely. So here I need to add more power through the pump, heat the fluid up, and then come down through the turbine. So I do have to increase the amount of power I put into the system to employ this strategy, but I still end up increasing thermal efficiency. So there are limitations. Ideally, I would increase T hot up to infinity, but I can't really do that because that T hot is the temperature that comes out of the boiler or the temperature that goes into my turbine, and I need to make it so neither of those components melt because of the fluid that's running through them. So I've got to be friends with some materials engineers who are always making better steels. I also am limited. I can only really heat this working fluid up to the temperature of combustion of the fuel that I'm using, or maybe the temperature of heat addition from something like a nuclear reactor. The other thing that the Carnot efficiency equation tells me is that I can improve efficiency by reducing the cold temperature in my cycle. To do that, I want to drop the pressure where I'm condensing the fluid, because this condensation happens mostly under the vapor dome, and if I drop this temperature, then I move to a lower pressure as I'm condensing my liquid. The temperature on the cold side of a Rankine cycle is typically limited by the environment. But if I can drop it, what happens is I increase the power generated by the turbine faster than I increase the power required by the pump. So those are two strategies that I can use to increase my thermal efficiency. The third strategy I can use is I can increase complexity. Now we've talked a little bit about thinking of systems like Rankine cycles as a series of Lego blocks that we put together. And this 4-component Rankine cycle that we used last class is kind of like learning Lego by playing with Duplo. So in the next couple lectures, we'll learn how we can become master builders and increase thermal efficiency by increasing the complexity of our systems. We'll talk about this next time.